Dear friends, now welcome to the second module lectures on online course at Health Safety and Environmental Management in Offshore and Petroleum Engineering under the auspices of IIT Madras NPTEL program. We have successfully completed the lectures on first module. There were about 4 tutorials which you must have answered in the first module. You have been evaluated for them, which will also become a part of the major examination at the end of the semester. We will now move on to the lectures on second module. The second module will focus on accident modeling, risk assessment and management. In the second module, the first lecture will now focus on safety regulations and dose assessment. The moment we talk about safety regulations with respect to dose assessment, we are entering into intricacy of process safety management, where we will talk about chemical exposure index or chemical risk analysis, etc. in this module and subsequently in the lectures in this module. Let us quickly see what are the objectives of the lectures on the second module. We will try to provide you an overview of dispersion release models. We will explain detailed understanding of chemical release analysis. We will also present few case studies in the process industries, how to do risk analysis for process safety management. We will provide you an overview of fire and explosion release models. We will talk about flammability diagrams and enable you to understand the use of flammability diagrams in mitigation or prevention of fire and explosion problems in process industries. We will talk about fire and explosion prevention methods in this module, and we will finally discuss some examples on event tree and fault tree analysis in this module. Let us principally ask a question: what do we understand by safety regulations as applicable to process industries like offshore and petroleum industry? Safety is essentially characterized by International Electrotechnical Commission, what we call briefly as IEC standards. IEC standards are extensively used as a benchmark standards in oil and gas industry. IEC 61508, which talks about functional safety of electrical, electronic, programmable electronic safety related systems, released in Geneva 2000, is a very good handbook, talks about functional safety of these process industries. IEC 61511 also talks about functional safety related to instrumented systems in process industry, which is also released in 2003 in Geneva. IEC standards are, dear friends, voluminous and lead to extensive process and design inputs, based on which safety implementation becomes instrumental and very decisive. IEC standards are actually based on familiarity and definition of equipment under control. So, it is important for us to understand what are those equipments we deal with, that of the standards to be emphasized, and we should be familiar with the operation of the equipments where we are imposing safety standards. You should be capable of identifying the hazards given in the process system. You should also have a prerequisite idea about interaction between the equipments under control. It is very important that what would be the overlay of one equipment, working of one on the other, is important to understand the safety emphasis on different equipments working in series. Ultimately, one should focus on risk assessment under process equipments, which is covered in this module. Interestingly, when we talk about safety evaluation, it is important for us to understand all safety evaluations need to be carried out in a very generic manner. Safety regulations and evaluation should not be problem specific, because you must apply a generic rule to approach the problem in a more prescribed manner. It is essentially because of certain reasons. Only few details about installation shall be available to you in the early conceptual stage, because when the process starts, as the process becomes complex because of the operational temperature and pressure variations, it is very difficult to foresee the hazards in the beginning. So, you will have only very few details about the installations with you, which will talk about the mechanical configuration specifications of the equipment, the working principles, working temperature and pressure, etc. In case of pressure and temperature being violated during the operation or during the process, it is very difficult that you will not have much details about these installations at those high pressure temperature functioning. Therefore, in the early conceptual stage, you will not have much details about the installations, and hence decision makers have to rely upon the knowledge from other similar projects. Therefore, IEC standards invoke such generic understanding on safety regulations, and it is always experience packed decisions which will improvise safety for equipments under operation in process plants. Alternatively, friends can also use OLF guidelines, which will give you a simplified requirements of oil and safety. OLF guidelines are generally given by the Norwegian Oil Industry Federation, which is also called as Norwegian Oil Industry Association. OLF guidelines eliminate the need for extensive analysis. They are more or less prescribed rules which has got to be followed for safety improvisation in oil and gas industries. In addition to that, we also have something called safety integration limits, which comes in 3 stages. They are categorized as SIL level 1, level 2 and level 3. Let us quickly see what do we understand by SIL level 1. SIL level 1 means it is the required maximum unavailability of the equipment on demand is 10%, whereas if the unavailability on demand is 1%, we call that as SIL level 2, and if the unavailability is on demand is about 0.1%, we call that as SIL level 3. One can easily remember these numbers 1, 2 and 3 related to this percentage when you see this slide. SIL levels are also expressed as 10%, which is 10 power minus 1, that is 10 by 100. Similarly, 1% becomes 10 power minus 2 and 0.1 becomes 10 power minus 3, and the numbers of these 1, 2 and 3 is what you actually see as SIL levels 1, 2 and 3 respectively. Now, for your understanding, let us quickly look at the table on the right hand side. For different safety functions, SIL indicators are shown in the table, which is extracted from the Oil and Safety Industrial Directive standards. Process segregation should have a safety integrity limit as 1, whereas blowdown is 2, and isolation of risers and gas detection is also 2 respectively. Now, what does this mean is, if the process segregation has imposed a safety integrity limit or level as 1, it means the process segregation can be maximum unavailable on demand by about 10%. So, if you have got, let us say 100 equipments in the pipeline to work at, 10 of these 100 can be remaining out of order. So, even if 10 on 100 scale remains out of order, one can say SIL level 1 is implemented in the standards, whereas the blowdown preventers, isolation of risers are maximum should be made unavailable maximum to a level of only 1%. So, as the SIL level goes higher and higher, you can see the equipment or the process importance gets deeper or more important in the process industry. As we said, in oil and gas industries, we have something called acceptable risk. We discussed about this in the first module as well. Let us quickly see how do we categorize acceptable risk in industrial standards. Risk is acceptable to regulatory agency and also to the public. According to the United States Environmental Protection Authority criteria, a lifetime risk of 1 in million is defined as acceptable for carcinogens, whereas for non-carcinogens the acceptable risk is hazard index lesser than 1, whereas according to UK Health and Safety Executive, the acceptable fatality accident rate is 1.0. If you look at the other international regulations, for example the Dutch regulation, the acceptable level of risk is given in a figure as you see here in the slide. It is closely related to the number of fatalities and the frequency of the event causing these fatalities. If the number of fatalities exceeding 100 and the frequency is about 1 10 power minus 5, which is as higher compared to that of 10 power minus 8, then we call this region as an unacceptable risk. Whereas if the number of fatalities is lower than 10 and the occurrence of those events causing these fatalities ranging from 10 power minus 6 to 10 power minus 8, we call that kind of risk in the plant as acceptable risk according to the Dutch regulations. So, dear friends, depending upon the country's stringent regulations imposed on process industries, the acceptable risk level in process industry also varies. As far as India is concerned and in general global considerations are there, we consider what is called as ALARP triangle as an acceptable norm of risk. ALARP is expanded as low as reasonably practicable, but we also say is an acceptable standard. So, as low as reasonably practical. The ALARP triangle has got 3 distinct segments as you see here as painted green, yellow and red. The red zone is indicating intolerable risk. It means on any cost risk cannot be justified if the risk falls in this criteria. However, if a risk falls in the green criteria, it is broadly acceptable region. Therefore, there is no need to work for detailed demonstration of ALARP when the risk falls in this criteria. Most of the cases in oil and gas industry, the risk will fall in a larger domain which is marked as yellow here, which is called as an ALARP region. So, if the risk is tolerable only if the cost is grossly disproportionate to its improvement. For example, you have got a risk identified in a given process industry, you want to eliminate the risk completely, but the cost involved in eliminating that risk is highly disproportionate, then you accept that risk as a part of your process industry. So, risk is undertaken in such cases only if the benefit which is from the cost of control of risk is desirable. So, you decide how the risk is acceptable dependent on the financial regulations and the benefit drawn from the financial imposition on the risk level. Dear friends, please understand, in oil and gas industry the acceptance level of risk is also related to the economic viability of imposing and the risk in terms of its mitigation. However, it is interesting for you to know risk is there in every walk of life. For example, cigarette smoking, for example, accidents while you travel in automobile, in railway, even when you stay in the house, there can be risk which is categorized, which is also declared as acceptable societal risk by the public. For example, smoking 30 cigars per day will give a risk of 1 in 200, motor vehicle accident is 1 in 10,000 and so on, as you see in this slide. Even rail accidents will also have an acceptable level of risk. It means risk is an acceptable format in every walk of life. It is not only acceptable in oil and gas industries as you may perceive as a wrong idea. When we talk about chemical risk, especially when we talk about process safety regulations in process industries, we underline what is called inherent safety, which is imposed in chemical plants or process plants. The aim of inherent safety is basically to prevent accidents instead of relying on the control systems. It is very intelligent way of improvising safety. You prevent accidents instead of controlling them after they occur. It includes reducing inventories of hazardous materials, use alternative process route involving lower pressure or more moderate temperature in a process routine. The catchwords of inherent safety as defined by OSHA, OSHA expands for occupational safety and health administration are the following: minimize the risk, substitute the process deviations, moderate and attenuate or limit the effects or consequences caused by the moderation, and simplify or make it error tolerable. So, these are the keywords what the inherent safety means as per OSHA recommendations. The moment we talk about safety in chemical industries or process industries, which is as applicable to oil and gas industries, the moment we get in our mind is a release model. Now, what is a release model? Toxicology is a term which one has got to understand before understanding the release models or dispersion models. Then the question comes in mind, what is toxicology? Toxicology is defined as a qualitative and quantitative study of adverse effects of toxicants on biological organisms. Please understand, this is the domain of science which talks about the qualitative and quantitative implications of the consequence of toxicants on biological organisms. These organisms can be human beings, can be animals, plants, etc. So, the study deals with the consequence of effects, it is not dealing with the characteristics of the toxicants itself. Please understand, the term may reply or applicable to the chemical disposition, but it is the effect of dispersion of the chemical in the environment. A toxicant therefore defined as a chemical or a physical agent including dust, fiber, noise and radiation. All of them are called as toxicants. Toxicant does not mean only a chemical, it can be even a physical agent as simple as dust and fiber and noise and radiation effects as well. Now the question comes, how do these toxicants enter biological organisms? They can enter by ingestion, that is they can enter through the mouth into the stomach, they can enter by inhalation, they can enter through the mouth or nose into the lungs, they can enter through injection, they can enter through the cuts in the skin, they can be also dermal absorption, it can enter through skin membrane itself. So, toxicants can enter in human organism in all these four manners. Once we talk about toxicants present or dispersed in environment, then we are talking about acceptable level of safety. Now, integrating these two, let us talk about dose versus response requirements. These are two graphs which are shown to you, which will explain what is dose versus response in terms of acceptable standards. All biological organisms respond differently to the dose for which they have been inhered to. The same dose of toxicant can cause different variations in different organisms because of the following reasons. It can be due to age, it can be due to the sex, it can be due to the weight, diet, general health, etc. Therefore, a standard study has been conducted and statistical average has been taken, which is plotted as shown in the figure. One is a normal plot which shows the standard deviation, and these bars are all the variations along the line and the curve is plotted along its mean. The other plot is a logarithmic variation of the dose versus response in percentage varying from 0 to 100. Now, based on these two curves, we are going to define the acceptable standards of dose response on biological organisms. When we talk about various types of doses which are available in chemical industry, then there are three doses which can be explained in the literature: effective dose, toxic dose and lethal dose. In the same curve as we saw in the last slide, the logarithmic dose with respect to toxic response in percentage is indicative of ED, toxic dose and the lethal dose as you see in the picture here. Now, as far as ED and TD and LD are concerned, there are some standards called TD50, LD50 and ED50. It is very simple that the corresponding dosage of that effective dose will be a toxic response cost 50% of the population. So, 50% of the population toxic response is then projected to the respective curve and then projected vertical to get the corresponding dose which is responsible to cause a toxic response of 50%, and the dose can be either effective, can be toxic, it can be lethal. Now, the question comes, what do you understand by effective, toxic and lethal dosage? Lethal dosage is defined as the following: if the response is ultimately fatal or lethality, the response versus log dose curve is called lethal dose curve. If the response to the chemical or agent is minor and reversible, for example, the exposure causes you minor eye irritation, etc., the response log dose curve is called ED curve. The toxic dose is defined as the response to the agents if it causes undesirable response, that is not lethal but it is irreversible. For example, it can result in liver damage, can result in lung damage, etc. Then the corresponding curve of the response versus log dose curve is called TD curve. There is something called lethal concentration which is applicable for gases. This is logarithm of dose which is being used in the lethal concentration, which is applicable to gaseous states. Once we understand what are the different doses which can be toxic, we have also seen what are the different forms by which these dosage or these dispersed chemicals can enter in human organism. Then comes the question, what is the maximum value of these dosage which is acceptable as per the safety norms. Now we talk about threshold limit values, in short TLVs. TLVs actually represent conditions to which all workers will be repeatedly exposed every day without adverse health effects. Friends, please note, threshold value is a limitation imposed on exposure to a human being who is working in the plant without causing any adverse health effects. So, it is the consequence of the dose on human body, which is one of the safety regulations imposed by OSID. Therefore, for any dose value below this dosage, body is able to detoxify. It means for a given chemical, if you are able to explain the threshold limit value, if a human being or a biological organism is exposed to a value lower than the TLV, then it is understood that the body can be detoxified and it will not cause any irreversible damage to the body. Now the question comes, how do you estimate this? There are two agencies which can establish TLVs in process industry. One agency is the American Conference of Governmental Industrial Hygienists, ACGIH. The other one is OSHA, as we defined earlier. OSHA of course gives the value in permissible exposure levels, briefly called as PELs. Now let us see what are TLVs. There are three types of TLVs, namely as TLV TWA, TLV STEL and one more. TLV TWA is called time weighted average. This is an average of normal 8 hours working per day or 40 hours working per week for which the workers will be exposed. So, you talk about the threshold value in a time weighted average, you try to measure the exposure limits of the chemical on biological organisms like a human being for 8 hours or 40 hours a week and take an average. You call this as time weighted average of TLV. The other TLV value is called STEL, which is called short term exposure limit. The term short term itself is very clear that it is talking about the maximum concentration to which a worker can be exposed for a period only to a maximum 15 minutes continuously, but however within this 15 minutes he must not suffer intolerable irritation, chronic or irreversible tissue changes and narcosis of sufficient degree which reduces workers' efficiency considerably. If the worker is not exposed to these three consequences for 15 minutes, we call that as short term exposure limit of the chemical. The third one is called a ceiling point or a ceiling limit, that is called TLVC. It is the maximum concentration that should not be exceeded even instantaneously, that is even for a second this concentration value of the chemical should not be exceeded, because this will not be sustained by a human being or a biological organism. Now one can convert TLVs to parts per million or milligram per cubic meter. The conversion is actually based on 760 mercury pressure at 25 degrees centigrade with a molar volume of 24.45 liters. Now the equation for converting TLV, which is available in milligram per cubic meter, is given to you in the slide now. So if you know the TLV in parts per million, then if you know the gram molecular weight of the substance, then divide that by the molar volume of 24.45, then you can find TLV in terms of milligram per cubic meter. Alternatively, if you know the TLV in milligram per cubic meter, you can always cross multiply and get the equivalent TLV in parts per million. So TLVs are available for all chemicals in both the formats, either in ppm or in milligram per cubic meter. Once we understand what are the threshold values of different chemicals for which a human being can be exposed on a work environment, let us quickly talk about what do we understand by industrial hygiene. Industrial hygiene is actually a science devoted to identification, evaluation and control of occupational conditions that could result in sickness and injury. Identification deals with determination of presence or possibility of workplace exposure. Evaluation deals with determination of magnitude of exposure, and control deals with application of appropriate technology to reduce workplace exposures within acceptable levels. Let us quickly talk about identification in industrial hygiene. It requires a thorough study of chemical process, operating conditions and operating procedures which are applicable for a specific process industry. Now the question is, to identify a specific industrial hygiene problem, what would be the sources what you want to depend on? You must know the process design descriptions, you should know the operating instructions of the plants and equipment, you should have a very thorough safety reviews, and you can also collect this information from material safety data sheets which is available in the plant for every inventory. If we talk about evaluation of industrial hygiene, then it aims to determine the extent and degree of employees' exposure to physical and chemical hazards. Physical hazards can be evaluated by comparing the existing strength with that of the threshold value, whereas chemical hazards can be evaluated by comparing the concentration of toxicants within the allowable limits, as we saw in the previous slides. When we talk about potential hazard identification, then it goes by two ways. You can either do it by physical or chemical hazards. Talk about chemicals, then the following could be an hazard substances. It can be liquid, can be dust, can be gases and fumes. But in physical hazards, can be radiation, can be mechanical hazard, can be noise pollution, it can be pressure and temperature variations unacceptable to the human being. Now when you talk about the mode of exposure, it can be dermal contact through skins, it can be inhalation, it can be ingestion, it can be indigestion or injection. Now the damages which can result in an organ of a body can be lungs, ears, skin, nervous system, liver, kidney and reproductive systems. Now hazard identification is a combination of hazard identification and its consequence of exposure in human body, as you see in a given system. Now when we talk about exposure evaluation, we now focus on chemical hazard, because process industry like oil and gas industry is essentially focusing on chemical hazard. Let us quickly see how do you understand by chemical hazard and how do you evaluate it. For a chemical hazard, we try to work out what is called time weighted average concentration. The time weighted average concentration is given by the equation on the right hand side, which generally averaged for a normal working hours of 8 hours, that is why the denominator 8 is shown here, and which is having the integration of the concentration exposure for a weighted average of 0 to TW, where Ct is the concentration either in ppm or in milligram per cubic meter of the chemical in air, and TW is the work shift time in hours. For a discrete average of concentration, Ca can be over a period of Ti, as you see in this equation. For example, if the working time is not continuous and the chemical exposure is also not continuous, you can still find TWAC with the sum of average of this over a period of 8 hours. For example, the person is exposed for a specific chemical concentration for a specific period within 8 hours, you get the sum of this and take an average of this, that is why it is called time weighted average value. Based on this, one can also find out whether the human being is exposed to overexposure in the workplace. The workplace overexposed value is considered to be overexposure if the R value is greater than 1, where R is given by the ratio of CTWA by TLV. For every chemical, you have a threshold limit value. You have already know the CTWA value. If the ratio of this exceeds 1, then one can say the workplace exposure is highly overexposed. Sometimes in a chemical concentration can also have a mixture. So we can also work out the time weighted average of the threshold limit value for a mixture. For more than one chemical, the combined exposure can be multiple toxicants, which can be given by this equation, which can be TLA as you see here, which can be the ratio of the concentration of n number of chemicals, where n refers to total number of toxicants, and Ci is the concentration of the ith chemical with respect to the toxicants as TLV TWA for the chemical I. So, you try to work out this ratio. Now, you can find out the TLV TWA for a mixture which can be ratio of the specific concentration with that of the concentration available for a specific value, which is time weighted average. The workplace overexposure for mixture of multiple toxicants can also be worked out by calculating the R value, where R is now given by the equation as shown in the slide. If the R value exceeds 1, it is considered to be overexposed. When we talk about exposure evaluation of physical hazards, then we have noise problems, which is common in process industry. Exposure to noise are usually measured in decibels. Decibel is a relative algorithmic scale used to compare the intensities of two sounds. I is the concerned sound intensity. In I0 is the reference sound intensity. Then the noise intensity in decibel is given as the equation as shown in the slide now, which can be computed on a logarithmic scale. If you look at the acceptable level of the sound intensity in decibels for different processes involved in the industry, you can see here even whispering can also have a sound intensity of 20, whereas riveting, punch press, passing truck, etc. are have very high decibels of 120, etc. An acceptable level of sound intensity in process industry should not cross 90. So, if the value crosses 90, it is unacceptable, and the exposure to this sound level should be as minimum as possible under safety regulations of process industries. If you look at the sound level exposure in terms of the maximum permissible exposure, as the value of sound levels goes higher and higher, the exposure cannot be more than fraction of an hour. So, if you have a sound level of around, let us say 75 or 80, it is acceptable for 8 working hours. If the sound level goes above 90 decibels, then the working exposure hours should be as minimum as possible, which is imposed under the safety regulations of oil and gas industries. When we talk about industrial hygiene, we also talk about control. Two major control techniques are generally practiced. One is called environmental control, the other is personal protection. Environmental control, the main aim is to reduce concentration of exposed toxicants in the workplace. Therefore, the best idea is enclose the workspace or equipment under negative pressure, provide local ventilation in a very high manner, contain and exhaust hazardous substances. Dilute the ventilation, it means you must design the ventilation system to control low level toxicants. Use essentially wet methods to minimize contamination with dust. Good housekeeping, as we discussed in the first module, is one of the key tools to have very good control measures for environmental control. When you talk about personal protection, the aim is to prevent or reduce exposure by providing a barrier between the worker and the workplace. You can provide hard hat or helmets, safety glasses, chemical splash goggles, splash suits, earplugs, etc., which can act as a physical barrier which can protect the worker from noise and other physical hazards in the given workspace. Now, chemical plants are potential source of accidents, oil spill, fire, explosion, reactor runaway, and fugitive emissions are possible potential hazards which can result in the process industries, which can cause accidents. Mechanical hazards include improper maintenance, tripping, falling or moving equipment. Unfortunately, this will also add to as main contributors to spills, fire and explosion in chemical industries. When we look at the common types of chemical process accidents and categorize them as different accident type, look at the accident type as fire, explosion and toxic release. If you look at the chance of occurrence, fatality chances and chance of financial loss, for a toxic release in explosion, the financial loss is very high, whereas a fatality is only intermediate and low. However, we look at fire, the chance of occurrence is very high, which is indicating in red color, and the fatality chances are very high, but the financial loss caused by fire is not in the higher range but is only in the intermediate range. So, this is a graphical representation of different kinds of accidents happening in process industries and what would be the likelihood, the fatality and the financial loss related to these three varieties of accidents which are very common in oil and gas industries. Now, let us look at the elements to control a process accident. If you identify an hazard, it will have an initiating event. The initiating events can be intermediate events or propagating events. It can be mitigating events. So, one can always see the propagating events can also lead to accident consequences. So, hazards can be actually resulting in initiating events, and adding together the propagating and mitigating events together interact to form an accident consequence which need to be controlled. Now, let us quickly see what are the type of hazards what we can see in an oil and gas industry: flammable material, combustible materials, toxic chemicals, unstable materials, highly reactive reactants can be examples of hazards. If you look at initiating events, they can arise from equipment malfunctioning, containment failures, thermal runaways, human error in operations and maintenance, etc. If we talk about intermediate propagating events, they can be process parameters like temperature, pressure, flow rate, etc. It can be deviations from the design intents, it can be toxic materials, can be reactive materials, can be ignitable and explosible materials available as an inventory in the process plant. If we talk about mitigating events, it can be arising from safety system responses like relief valves, grounding, backup, utilities, etc. It can be mitigation system responses like vents, blowout valves, containment dikes, flares, sprinklers, etc. Can also be from contingency operations like alarms, emergency procedures, personal safety equipments, evacuation plans, security arrangements, etc. If we talk about the accident consequences, the consequences will be only three, which can be either fire or explosion or release of toxic chemicals in the environment. So, friends, please understand, this is a very comprehensive table which gives you what are the possible source of hazards, what could be the initiating events, what could be the propagating events, what can be the mitigating events. If they are all not under control, what will be the consequence accidents what we get. So, it is very interesting, instead of protecting the equipments after the accident, it is always better to design a system to prevent accidents. So, identify the propagating and mitigating events, have an effective control mechanisms so that these kind of mitigating events are working in a proper manner where the design is effective to control accidents. Now, let us quickly see what are the steps involved in risk analysis of process accidents in particular. Predict the accident occurrences and the damage potential, reduce the risk well in advance before an accident could occur, ensure system safety during operations, and the plan accident prevention based on the answers to the following questions: what are the potential hazards, what can go wrong and how, what are the chances of their occurrences, and what are the consequences if they occur. What are the different methods available in the literature for performing chemical risk analysis? There are different qualitative risk analysis methods. They are used to predict undesired situations of the process system. They are helpful to identify the potential hazards, both chemical and mechanical. Some of the examples are HAZID, HAZOP, PHA, FMEA, etc., which were discussed in detail in the last module. If we talk about quantitative risk analysis methods, they are used to evaluate likelihood of occurrence of accidents. They find the specific causes and consequences of potential hazards along with their contributions. They are used to evaluate the effectiveness of control measures and design modifications in the process system. They use probability theory, therefore, they are called as probabilistic risk analysis also. Examples are FTA and ETA, where they stands for fault tree analysis and event tree analysis, which are used for identifying the causes and consequences of an accident. We also discussed about safety review in the first module. Let us quickly see what would be a safety review program. There are two types of safety review program. One is informal safety review. which generally applicable for small changes to the existing process industries. Small bench scale laboratories can be applicable for this kind of safety review program, or is a formal safety review program which generally used for new process for certain or process which has got huge modification in the existing system. It requires a team of experts which need to develop and review the report and inspect the process periodically. We can also do process hazard checklist, which is helpful. It is actually a list of all possible hazards that a reviewer needs to consider. The checklist contains probable consequences of identified hazards. All enlisted hazards may or may not apply to the situation. However, the checklist should remain area of concern to the operators. It should stimulate the operators or reviewers thought process very carefully. It can be applied to design conceptualization, can be applied to pilot plant operation, at the detailed design stage, at a routine checking itself. It can also enter into system design modification expansion stages. It is most importantly applied in the decommissioning stages. One can also conduct hazard surveys, which is essentially a technique to identify and rank the hazards quantitatively. It is simple if the method involves only the survey inventory of hazardous materials in a given facility. Examples: Doe Fire and Explosion Index, Doe Chemical Exposure Index, which is called CEI, which we will discuss in detail in the next lecture onwards. CEI is one of the popular method of toxic release and dispersion models practiced in oil and gas industries. Chemical Exposure Index is essentially an outcome of a result of many petrochemical incidents occurred in the 1980s. Chemical Exposure Index Guide is developed in 1986, which is used as a procedure to evaluate risk analysis in process industries. It is a very simple method of rating the relative health hazard to people residing in the area where the process industry is located. What can a chemical exposure index give me? CEI gives me the risk index value, which is mere number which is relative to the various safety and environmental characteristics around the plant where it is situated. It can be used for risk ranking or various options of safety aspects in a given system. This index value is used along with the decision analysis tool to check whether the process options in a safety system is okay or not. It addresses both process and personal safety. What do you actually need to do a chemical exposure index analysis? You require the plan of the process plant. You also require details of surrounding area in terms of population. You require a flow sheet which involves major piping, location of containment vessels and their capacities, and most importantly a list of chemical inventories present in the space of the working plant. You require to identify the physical and chemical hazards from a given properties. You should also know the physical, mechanical and chemical properties of the material which is being investigated in the given plant. You should also know ERPG values. ERPG stands for Emergency Response Planning Guide, which tells me what are the ERPG values for different chemicals available in the inventory. Once you know that, you follow the CEI guide and calculate and fill up the CEI form and try to evaluate the safe hazard distance for a given chemical if it is exposed in the environment. We will take up an example in the next lectures and see how CEI can be done for process industry. Thank you very much. We will see in the next lectures.